Hello and welcome. Today we're looking at Organic Chemistry 1 Review Part 1. Question 1. Circle all the structures that are Lewis acids. If you look at the first structure, it's a proton, hydrogen with a positive charge, and Lewis acids accept electron pairs. So if you look at that, that will accept an electron pair to form a bond. So that's a Lewis acid. The second structure is a methoxide, CH3O-. That one will donate electron pairs. So that will be a Lewis base, not Lewis acid. The third structure, ammonia, NH3, has electron pairs and therefore it's going to donate electron pairs. So that will also be a Lewis base, not Lewis acid. And the last structure is a hydroxide ion, OH-. That will also donate electron pairs and therefore it will be a Lewis base. Question 2. Write a ground state electronic configuration or electron configuration of chloride with a charge of -2. So chlorine ion with a charge of -2. If you look at the periodic table, you'll see that chlorine has 17 electrons, but chloride with a charge of -2, the only way you can have a charge of -2 is if you have an excess of 2 electrons, so that means you take 17 plus 2, and now you're looking at 19 electrons. So chlorine with a charge of -2 will have 19 electrons. So we're going to write electronic configuration for that, and we start filling the electrons starting from the lowest energy level, which is a 1s, with a maximum of 2, so that's 1s2. Then we move to the next level, 2s2, that's the lowest energy, and then the next one is the p level, 2p, and remember we have px, py, and pz. Each of those have a maximum of 2, so that adds to a total of 6 electrons, so 2p6. Then we move to the next one, 3s2, and then 3p6. Then after that, we don't go to 3d because actually 4s has a lower energy than 3d. So we put the remaining 1 electron on the 4s orbital. The other way to write this electronic configuration is to use what we call inert gas core structure, where if you look at up to 3p6, actually that's the electron configuration of argon. So we write argon core structure, and then the remaining orbital is 4s1. Question number 3. Which of the bonds shown below is a polar covalent bond? So if you look at the first one, number 1, it's oxygen-oxygen double bond. The only way you can have a polar covalent bond is if there is a significant difference in electronegativity between the two atoms. So because both atoms of oxygen have same electronegativity, there's no electronegativity difference, so that's a non-polar covalent bond. In fact, it's a symmetric covalent bond. Number 2, you have nitrogen-nitrogen triple bond, same thing as oxygen-oxygen double bond. The two nitrogens have same electronegativity, so that's non-polar. Number 3, we have hydrogen-carbon bond. If you look at the periodic table, hydrogen is on the left, while carbon is on the right. So as you go to the right, the electronegativity value increases. But the difference in electronegativity between hydrogen and carbon is below or equals to 0.4. Anytime you have difference in electronegativity value being 0.4 or lower, then that's considered a non-polar covalent bond. So number 3 is a non-polar covalent bond. And then the last one, number 4, is nitrogen-hydrogen. Again, hydrogen is in group 1A, while nitrogen is group 5A. The difference in electronegativity is significant. It's above 0.4. And therefore that will be a polar covalent bond. And one way to show the bond is polar is to use a dipole arrow, the one shown in red, where the head of the arrow faces a higher electronegativity value atom, which is nitrogen, and then the tail with that cross to make it look like a plus faces the lower electronegativity atom, which is hydrogen. So number 4 is the answer. Question 4. Which is a stronger acid? An acid, Hd with a pKa value of 20 or Hb with a pKa value of 10. What you need to remember is that stronger acids have higher ability or to donate hydrogen ions. So they donate hydrogen ions easily, and therefore they have lower pKa. And remember, pKa equals negative log of Ka. So that means lower pKa will be higher Ka, where Ka is the acidity value. Higher Ka means higher concentration of hydrogen ions. So stronger acids have higher Ka and lower pKa, and they have higher hydrogen ion concentration. So Hd has pKa of 20, while Hb has a pKa of 10. So you can see that Hb has a lower pKa and therefore Hb is a stronger acid since it has a lower pKa. Question 5. Draw all the possible resonance structures for the following. Remember to use resonance arrow or arrows, and also use arrows to show the electron flow. So if you look at the structure on the left, you always start from a higher electron density or a higher electron concentration. In this case, you're going to start from the double bond, and you have two double bonds on the right and on the left of that positively charged carbon, that is also called a carbocation. So the positively charged carbon has lower electron density. Actually, it's electron poor. And in this case, the electrons are going to flow from either of the carbon-oxygen double bonds towards the carbon with a positive charge. So I chose the left-hand side carbonyl, carbon-oxygen double bond, and then moved one of the bond electrons, which is actually 2 electrons, and that moves to form a double bond between that carbon that was originally carbonyl carbon and the positively charged carbon. And when you do that now, move to the next structure, you have to use a resonance arrow, the double-headed arrow. The oxygen on the left is electron poor, and therefore you put a formal positive charge on that oxygen. You could actually show all the non-bonding electrons to help you keep track of the electrons. And then now, starting from the left, the double bond, again we move one of the double bond electrons, that's 2 electrons, to form a double bond. Then at the same time, if you look at the middle structure, the red double bond, that means 2 electrons, move to form a bond between carbon and the oxygen with a positive charge to give the structure on the right. Always remember to use the double-headed arrow, which is also called resonance arrows, when drawing resonance structures. So this structure has 3 resonance structures. Anytime you have more than one resonance structure, it makes that structure more stable because you're able to delocalize the charge. So in this case, you have a positive charge, a carbocation, but because of resonance, we can delocalize the positive charge between the 2 oxygen atoms, making it more stable, because then the charge is evenly distributed between multiple atoms. Question number 6, briefly describe what is a rearrangement reaction. So if you start with a reaction where the atoms are connected as given here, A, B, C, A connected to B, connected to C, and then after the reaction, you realize that you did not lose or gain anything. You maintain the same atoms, but now you see that A is connected to C and C is connected to B. So we've changed the order of connections, and that's a rearrangement reaction. So it's a reaction where the only change is how the atoms are connected.